Okay. Just to illustrate an example of this type of pressure volume behavior that we talked about at the critical pressure and temperature of a compound. This is an example for ethane, and this is taken from the monograph in chapter 2, figure 2.7. And what you see is this is pressure versus volume. This is now a mass volume. It doesn't really matter if you're using mass volume or molar volume. And you can see at the temperature of 90 degrees Fahrenheit, which is approximately the critical temperature of ethane, you can see that the volume is coming down quite, vertically, pretty much straight down here, and then it turns the corner, becomes more or less flat at this point here, the derivative, and then continues its track downwards towards behavior that's becoming more like ideal gas behavior out here at low pressures, lower and lower pressures. And in this region here, clearly it's behaving like a very slightly compressible liquid because it has such a abrupt derivative. And here the critical pressure of ethane must be around 710 psi A, and the molar density down here about 0.075 pounds or cubic feet per pounds. So, well, this is just an example from the book related to that. One good question during the break was that how do you calculate for mixtures? Do you calculate like an average pseudocritical temperature and average pseudocritical pressure like we did for the Standing Cat's Z-factor method? And the answer is not exactly, but we do calculate an average for a mixture. So let's just say, as an example, if we've got a mixture, I'll use this UI. It could be either a gas composition or an oil composition or a water composition. I'll just use the UI. The way van der Waals and recommended applying this equation to a mixture, a particular phase made up of a mixture. So the average A is calculated for that particular phase. Phase P being either gas or oil or water. He gave a method for calculating the average A and the average B of that phase. The B is the simplest. It just takes the mole fraction times of the component I times the value of B for component I in a so-called linear mixing rule for all of the components. We might have 10 components or 40 components or 100 components, however many components is describing your system. For the A average, for reasons I can't even explain to you, I mean, smart thermodynamicists can, and van der Waals certainly could if he wasn't, 6 feet under. You use what's called a quadratic mixing rule in order to be thermodynamically kosher, okay, to get the best results from a thermodynamics point of view. So here you take the mole fraction UI times the mole fraction Uj is a double summation times AI times Aj, and we have to take the square root of that to get our units back in place. And that's a quadratic mixing rule. So that you can take a gas composition like we looked at for Troll, throw in the gas compositions, you can find A and B for methane, ethane, propane, because we know the PC and TC of each of those. and find the A's, and then you can come up with the A and B for the troll field, for the troll gas. Okay? So it's relatively simple. You know, AI becomes, you just have to know the critical properties of the component I here. Any questions? So that's application to mixtures. This is a particular phase. Okay? You don't apply, well, you can apply the equation for a total system, but it's we'll not get into that. Basically, you have a phase. You might have two phases, in which case, you know, you'll have to calculate gas phase and oil phase, composition yi and xi. So you'll have, basically, you'll have an A for the vapor, instead of using G, an average A for the gas phase. I guess I can write it this way. Sometimes you write it vapor for, and you'll have an average B for the gas phase. And here you'll have an average A for the oil phase and an average B for the oil phase. Okay? And you apply the equation to each phase, in a sense, separately. Okay. So, so let's just talk briefly as an introduction to phase equilibrium, thermodynamics, chemical equilibrium. Let's introduce briefly the basic phase equilibrium behavior of a pure component. Okay, so we're going to basically look at single component phase equilibria. Chemical equilibrium, phase behavior, all these terms that we're using for basically looking at what phases do we have, how much of each phase, and what is the composition of the phases. And let's start by using the water molecule as our example, because we're most familiar with water, okay, with H2O. And what I'm going to do is I'm going to plot a pressure versus temperature here. I'll use atmospheres and degrees C, just because you're probably familiar with those. And I'll put 1 atmosphere, which is what we're feeling here, and 100 degrees C, 200 degrees C, and so forth. Now, at 100 degrees C in 1 atmosphere, what happens with water? Water boils. Liquid water boils into steam water, right? Liquid water boils. Another way of saying it is that if you have a bunch of steam, that the steam could start condensing into the liquid water. That's not usually how we get to the liquid water. We usually start with liquid water over here at this temperature here, out of the faucet, right? That comes out of the faucet. We turn on the kettle. Starts moving its way, not in pressure, but it starts moving its way to the right in temperature. And then when that liquid gets to 100 degrees C, some of that 1 liter of liquid that we put in the kettle starts disappearing, okay, as steam. The water molecules disappear as steam. And that is what we call that water at 1 atmosphere and 100 degrees C. The molecules are equally happy. Remember the happy term, you know? Okay? Their energy, in a sense, is at a minimum. Okay? Their stress is at a minimum. And they don't care if they're in the liquid water boiling, hitting your cup, or in the steam leaving the kettle. Their energy, the degree of happiness is exactly the same. The water molecule doesn't care if it's in the liquid water or the steam. It has the same energy at 1 atmosphere. Okay? So basically at this condition here, which I'm going to sketch, that water, which might be at 1 liter in the kettle. Okay. And what you've got just the first bubble of steam, leave it just as it starts to boil. You got 1 little bubble. And if you were to look at the water molecules in that bubble of steam, their chemical energy, whatever that is, would be exactly the same as the chemical energy of the water remaining in the kettle. Okay? And in fact, there might be 3 molecules that make the first bubble. It takes a few of them, a few molecules, maybe 3,000 or whatever. Let's just say 3. Well, what will happen is that if you confine the volume, you don't let the steam escape, you confine the volume. So now you're at 1 liter plus a little bit more, where the little bit more is this bubble of gas. Okay? 1 atmosphere, 100 degrees C. What you'll see is that those 3 molecules that are in the gas bubble don't necessarily have to stay in the gas bubble. If one gets tired of being in the gas bubble, misses mama, jumps back into the water, liquid water, to visit mama, somebody else from the liquid water, some other water molecule, Tom, has to jump into the gas bubble. That's the only way. So Jane has to agree with Tom. Tom is in the liquid water. Jane is in the bubble. Jane wants to visit Mom. Jane jumps out, but only after agreeing with Tom that he will jump into the bubble. Okay? So it's not like you're put in prison in the bubble. And these molecules are jumping in and out because they're equally happy. Okay? As molecules. They don't have feelings about Mama. Okay? But nature requires that if one of the molecule jumps out of the gas bubble into the liquid again, then there's going to have to be another molecule of water jumping from the liquid into the gas bubble. Okay? That's good. Mother Nature's going to take care of that. But at that same condition, if we had a larger volume, let's say 10 liters, okay? So now what's going to happen is that there's going to be this much is still left in the kettle as liquid, okay? And this is now our steam, okay? We're still at 1 atmosphere, still at 100 degrees C. The molecules all have the same energy. They're equally happy. No big deal. Nobody kind of really knows what's going on. It's just that you have more of the molecules in this steam phase, and the liquid phase is probably down to about maybe 0.8 liters. Okay, and you got 9.2 liters of steam. And then what we do is that we increase the volume yet again, and we increase it I'm going to kind of like do it this way, to 1,000 liters. 1,000 times the volume. And now what we're going to see is that we're going to basically have 1,000 liters of steam and one remaining drop. Our coffee, we don't have enough for making a cup of coffee. Okay? We just got one drop of water left, with 3 water molecules in that drop, or 30 or whatever. Okay? So that's now gone down in terms of liquid down to some epsilon small amount. Any questions? This kind of is high school chemistry, but it probably is not described in this way. Okay? So the chemical energy of the system is changing radically, a factor of 1,000. The volume is changing. Okay? But nothing else in the system is changing. The properties of the steam don't change. The properties of the liquid don't change. About 1 centipoise on the water, 0.01 centipoise on the steam. Okay? But how does the equation of state come up with that? The fact that we've reached that condition where we create 2 phases. And how can the equation of state find out whether we've got 1 liter, 10 liters, or 1,000 liters? And if we have 10 liters, how does it know it has 0.8 liters of water, liquid water, and 9.2 liters of vapor? Okay? How does it do that? But the equation of state, in fact, does do that for a pure compound. I'm just going to kind of sketch how it does it in a sense. Okay? And before I go there, I'm just going to say that if you were at a lower pressure, right? You climb the mountains in Norway, it's a little bit lower pressure than 1 atmosphere. Water's going to boil at a higher or lower temperature. A little bit lower temperature. Okay. So there's actually that would be down here somewhere. So there's actually a line that goes here. It won't be linear like I'm drawing here. It might, on a linear scale, it might look something like this. And this line that passes for the different temperatures through the pressure where you get the same phenomena going on, that the water can split into a vapor or liquid or some mixture, it doesn't care. This is called the vapor pressure curve. Okay. It's where a liquid will form its first bubble, or a gas will form its first drop. Okay? The vapor pressure curve. Now, all compounds have this curve. Now, what's interesting about the curve is that if we look at the ratio of density, the density of the steam, the density of the liquid to the steam. Let's just look at the density of the liquid water to the density of the vapor, okay? Steam and liquid. It's about 1,000 kilograms per cubic meter. Liquid water, right? We all know that. And vapor, you may not know it, is around, at atmospheric conditions, about 1 kilogram per cubic meter. It's not exactly, but it's approximately. So the ratio of liquid to vapor density is about 1,000 here. I'm just going to put that in red. Or maybe I'll put it in black. That ratio is 1,000. Okay? But as you climb up this curve here, and you get to another point here, a higher temperature, and you see the same kind of phenomena going on. You can have either all vapor, all liquid, or half and half, whatever you like. But if you look at the properties, what's happening is that you're going to higher pressure and temperature. The gas density is going to be higher, but the oil density is not going to change that much. So the ratio now is only going to be about 100. Okay? Essentially because the gas density's gotten about 10 times higher. It's about 10 kilograms per cubic meter, whereas the liquid is probably still around 1,000. You keep going up here, you finally get to something that there's only a contrast of 10 between the liquid density and the gas density. So this liquid and gas start looking more and more alike in terms of density and viscosity and any other property. Okay? And then you get close to this final point, which I'm going to draw as that, and that is the critical pressure, and that's the critical temperature down here. Okay? As you just approach that, this ratio is going to get close to 1, very, very close to 1. Okay? 1.x, 1.1. As you get closer and closer to that, and as you reach that point here, the critical point, the ratio becomes 1. Okay? Now it's going to be difficult to see, you know, because the properties of the difference. You can't have a very, you know, the volume change can't be very much, but when you get real close to that, you can change the volume a little bit, and it goes from being all steam to all liquid, and they're so similar in properties you can't probably even see a meniscus between the two, an interface. So the interfacial tension, for example, approaches 0 at that point. Okay? Whereas the interfacial tension down here might be a value of 100. So this vapor pressure curve, our equation of state, if it's going to do what we're supposed to do, is supposed to be able to tell us what that vapor pressure curve is. It's supposed to tell us what the density ratios are, and so forth, along that curve. And that's just for a pure compound. Okay. Any questions about this? Anything that's now I'm going to throw something at you with regarding phase definition. A phase definition. This is going to kind of mess up your minds a little bit, because you think that this air that we're breathing is a gas, right? Yeah? You think that. But I'll argue until, you know, I hit 6 feet under, you know, and it may not be that far away, but I'll argue this is not a gas. Okay? You can only formally define a phase as gas phase if it is in equilibrium with a liquid phase. Okay? Well, there is a liquid phase here, okay? My cup of coffee and you know, some of your water bottles. But if we walked away from this room, taped it all up, sealed it off, I can pretty much guarantee you that in hours or a day, or I'm not sure how long it would take, is that my cup of coffee would disappear. And your open bottles of water, that water would kind of equilibrate into the air. Okay? So once all that liquid had disappeared, so to speak, if my definition is right, is that you can't define this as a gas phase unless there's an equilibrium liquid with it, then we would be in this problem of the air in this room is not a gas. Does that bother anybody? A little bit. Now what you can say, and a more proper semantic would be, this is gas-like. The air is gas-like. Like meaning, well, that becomes a subjective definition. It's got a viscosity of around 0.01 centipoise. That's gas-like. Okay? A liquid viscosity is greater than 1 centipoise, what runs out of the faucet. Okay? You know, the viscosity is not liquid-like, it's gas-like. Okay? So the point here is that we cannot define what we have in our system, our kettle with a balloon on it. Okay? We can't define it as being a liquid. This water I turn on over here, well, yeah, it's a liquid, yeah, kind of, but not really. Okay? If you equilibrate it with you put it in a bottle, you shake it up. You take one of your bottles of water, you shake it up, you seal it off, you shake it up, and you see two phases. Then you can say the water is liquid, and the air in the top is gas. That's fine. You've equilibrated. But this room is not equilibrated. And it's very unlikely that it's going to, if you put the water that's in here open, I think it'll probably absorb most of that water. Maybe not. If we come back 10 days later and there's still some water in our cups, then yes, the air is gas. We've got in equilibrium with the liquid water that's left. We're all happy troopers. But if all the water disappears, we can't say, at least formally, that it is a gas phase. You say, well, that doesn't really matter. I mean, normally you see pictures, you say vapor is over here. I'm sorry. That's wrong. Say liquid is over here on this side, and vapor is over here on this side. Okay, that's the way you see this picture drawn in 99% of the textbooks. Okay? But what you never see much, you don't see this big question mark up here. Okay? Because people like things to be black and white or clear and, okay. But there is a big question mark up there because what is it? Oh, they give it a name. Supercritical. That's not a phase. There is not a supercritical phase. There's a supercritical tag, name tag, but there's not a supercritical phase. It's gas or liquid. Okay? So we don't know up here what it is. Okay? But in reality, we really don't have a formal definition unless there are two phases together. This is vapor, this is liquid-like. That you can say. This is vapor-like, but only along the curve here where there are two phases. Only along here do you actually have vapor and liquid well defined. Okay? And those phases, the vapor phase, the steam is saturated. We call it a saturated phase. What is it saturated with? What is the steam saturated with? Liquid water. And we can say the liquid water is saturated. It's a saturated liquid system. But what is it saturated with? It's saturated with steam. You can't pump any more steam into that volume of liquid. So along here, we have what's called saturated vapor and liquid along that curve. And everywhere outside that line, we actually have a system from the lower left. I should probably draw it like this. Under saturated. Question mark. Not a formal phase. It's just an undersaturated phase. That's what you can say. The properties might look liquid-like, they might look vapor-like, or they might be out here in the range where we don't know what the heck it is. So phase definition, formal thermodynamic phase definition requires that there be two phases together in equilibrium. Okay? Okay. So how does the equation of state come up with this for example, in this picture, you can see that they've drawn this line from A to B to D. This is this is a saturated condition. So this would be for this particular component, ethane, at this temperature of 60 degrees Fahrenheit. This is the properties of the saturated cubic feet. So this would be saturated vapor and this would be our saturated liquid of ethane at 60 degrees Fahrenheit, and it's at 490 psi. That's the vapor pressure. So here we've got the vapor pressure, component C2, at a temperature of 60 degrees Fahrenheit is equal to about 490 psi. And this volume here, that's the inverse of density, mass density. So it's about 0.2 on the vapor. So if we turn that upside down, the mass density of the vapor, saturated vapor, is about 5 pounds per cubic feet. And the saturated density of liquid is about 0.04. Flip it upside down, and that's 25, right? 25 pounds per cubic feet. So that ratio I was talking about at this particular point on the vapor pressure curve at 60 Fahrenheit and 490 psi, that ratio is about 5. Okay. I'm going to bring this one more time into and I'm going to show you what the equation of state does, okay? Just because you must be curious. I'm hoping you're curious. Okay, we're going to look at 60 degrees Fahrenheit, okay? At 60 degrees Fahrenheit. We know the vapor pressure is around 490 psi for ethane. And we know that the actual measured, because this is based on measured data, the actual measured data looks something like this. You know, the volume hardly changes at all until we reach this point here. Okay? So if we start the experiment at 60 degrees and 900 psi, and we measure the volume, it's, you know, short of 0.04 or something, and we lower the pressure, we see that there's very, very little expansion, very small compressibility. Okay? It expands very little. But then it hits 490 psi. Okay. Now that volume starts increasing along here. Pressure doesn't change. I don't know what's special about D. And we move all along here until finally we reach this volume 5 times larger. Pressure hasn't changed. Temperature hasn't changed. And now we're with a vapor and one little drop of liquid. Whereas over here, we had this little volume with just a bubble, and now we've got something over here that's 5 times bigger with just a drop of liquid. So the equation of state, what does it look like? Van der Waals or Peng-Robinson or SRK? Well, there is no mathematical function that goes flat like this and then continues down. If you find that function, analytical function, guarantee you'll get a Nobel Prize. Okay? But instead, what we have is an equation that's cubic in volume. Because if you go back and look at that equation, you've got RT, V minus B. I'm just going to use the van der Waals because it's the simplest. And then we can just write that as RT, V squared minus A, V minus B over V cubed minus B, V squared. And you can go on. And you'll end up with a term that's an equation basically like this, plus a second, plus this, plus a constant is equal to 0. You'll end up with a cubic equation, and it's cubic in volume. Okay, so this is cubic equation in volume. So what the equation, the cubic equation is going to look like is going to be something like this. I'll have to go to a little bit smaller form here. I'm going to give it the benefit of the doubt that it gets this right. The B value is right. We picked the right B value, for example. Okay, and this thing comes down like this, more or less. What color do I have? Purple. And then it's going to go down. It's going to keep going down. And it's going to come up like that. And then it's going to go off more or less the way it should out here. Like that. And I haven't quite drawn it the way I want it to be. Make it a little bit bigger here. Something like that. That's what the cubic equation is going to look like. Okay. Because that's how cubic equations look. They've got the, and they call this the van der Waals loop. Okay. But if you're clever in terms of finding what is the chemical energy, because the chemical energy is calculated from thermodynamics as kind of it integrates volumes and derivatives in a kind of complicated way. I'm not sure I can give that to you exactly, but we'll go off and find it. The equation for that, chapter 4. There it is. Well, we don't have it for a pure compound, unfortunately. We got it for mixtures. Here it is. Well, what you can see is that this term here, phi, is like the chemical energy, okay? And you see it's got this integration of volume from the volume you're at pressure and temperature to infinity, and you've got this 1 over volume here, and you've got pressure in here. And for a pure compound, it looks something like this. Basically, it's an expression that can be integrated, differentiated, and integrated analytically. But what you'll find is that when you do that, anywhere it calculates a point here, it will be able to calculate the energy. Okay, this is the chemical energy. Anywhere along here, even where it goes down here. This might even go to negative pressures, might even go below 0 pressure. So anywhere along here, it can calculate given that it knows pressure, volume, and temperature, it can calculate the chemical energy. And when you do that, what you'll find is that the pressure where the energy on the left side, this liquid-like, okay, these are kind of liquid-like, where the chemical energy on this left side, where it's behaving like a liquid, becomes equal to the chemical energy that's on the right side, over here, where it's behaving like a vapor or a gas. The pressure where that happens is the vapor pressure. Okay? So it calculates you can calculate the energy anywhere along here, but where it finds this on the left side and on the right side having at the same pressure. So at the same pressure they have the same. So like if we take this value, you've also got a solution over here. Well, let's not take that one. Let's take this one here. We've got a value of chemical energy here, and then we've got one over here on the right. Those two energies are different. Okay? These two energies, this energy here and this energy here, are different. But as you're approaching this 490 psi, you find that this energy equals this energy. And that is the pressure where you have a vapor pressure. Okay?
What was the last one?
Right here. Okay, it calculates the energy here, and at this particular pressure we find that that's equal to the energy over here. If we go a little bit below here, this energy does not equal this energy. There's only one pressure where the left and right side of the van der Waals loop has the same energy. And that's the vapor pressure. So that's how, graphically, that's how van der Waals could go in and find. And when you do that, and because this is the energy is given by an integration in volume, what you'll find is that when this volume here, you choose a pressure, and that will split the van der Waals loop into two areas. When this area here, above the line pressure and below the line pressure, when those two areas here are equal, that is the correct line. Okay? So this area on the left side is equal to the area on the right side of the loop. So you just you pick a pressure. So if we pick the pressure here, you go like that, and you'd clearly see you've got way much more area on the left than you have on the right. It's out of balance. And only when you pick the right pressure, 490 psi here, do you get an equal splitting of the van der Waals loop. So that's another way, instead of, I mean, it's a graphical way. Instead of doing that integration from V to infinity, you kind of throw away everything else between those to the left and right. So the equation of state, together with this formal definition of chemical energy that Gibbs gave us, and doing the integration, we can actually find where the equation of state predicts this line to go. Okay? So the equation of state will actually, now, because the equation of state is not perfect, what you'll find is that, you know, if the blue here is actual data, I'll go back to, okay, if this blue is the actual behavior for a component, the equation of state, as originally given by van der Waals, for example, it might do something like this. It will be right here, because we use the PC and TC to find A and B. So it's guaranteed to be right here, but at the other temperatures it'll be a little bit off. And there's some ways that they correct that, but we're not going to go into that right now. But it does a pretty good job, I mean, for being such a simple equation of state, to actually find where water boils at 1 atmosphere. Okay? So this is just an example of how you're able to use the equation of state to define where you have a saturated phase condition and where you have an undersaturated phase condition. It allows you to calculate the chemical energy that we need for our mixtures, and it does it all from that simple original equation of state given here. Okay. And all you need to know for each component is the A and the B, and to get the A and the B you need the TC and the PC for each component. Any questions then before we take a break?
You have used a Fourier series to approximate the actual lines?
Which lines?
But go to the horizontal line. Instead of used to be
I've never heard of anybody trying to do that. So. But like I said, you know, if you figure it out and apply it to thermodynamics, then you'll probably be looking at some nice prize. But you know, you also have to have something that's computationally tractable. So. Any other questions? Okay, we'll take a break.